So we've seen how to calculate the theoretical yield and the limiting reactant if we have moles. But again, in our lab, our balances don't measure in moles, they measure in grams. So then we have to add 2 steps to each of our calculations to convert the amount of each reactant to moles. Then we convert the amount of product into grams. So when 11.5 grams of carbon react with 114.5 grams of copper oxide, we get 87.4 grams of copper. Find the limiting reactant theoretical yield and percent yield, and we're given the balanced chemical equation. All right. The first thing that we want to do is we want to convert our grams of reactant to moles. So let's do the first one, carbon. We have 11.5 grams of carbon. And of course, we can't use this chemical equation yet. We have to convert the grams into moles. And we know there's 12.01 grams of carbon for every 1 mole of carbon. Now we can use our balanced chemical equation here, and we know that for every 1 mole of carbon, we get 2 moles of copper. So 1 mole of carbon, we get 2 moles of copper. Now, we want to see how many grams, right? So for every 1 mole of copper, we know there's 63.55 grams of copper. And this gives us 122 grams of copper. All right. Let us do the second one, which is our second reactant, 114.5 grams of copper oxide. And let's see what we get if we had that much. This is very similar to how we did our pancake problem. If you had 10 eggs, how many pancakes do you make? And if you have 3 cups of flour, how many pancakes do you make? We're doing the same thing. All right, so 114.5 grams of copper oxide, and we want to see that there is 143.10 grams for every 1 mole of copper oxide. And now we can use our chemical equation. For every 1 mole of copper oxide, we get 2 moles of copper. So 1 mole of copper, 2 oxide, we get 1 mole of copper. Okay? And final step, we want to go back to grams. So 1 mole of copper gives us 63.55 grams of copper. All right? And this gives us 102 grams of copper. Okay? That means, since this was the smaller amount here, that means this is our limiting reactant. Copper 2 oxide is our limiting reactant, just like flour was our limiting reactant. So no matter how much we have of carbon, we can't make any more than 102 grams of copper because we are limited by copper 2 oxide. And so this here becomes our theoretical yield. Now, we've answered this, our limiting reactant theoretical yield, but what is our percent yield? Remember, your percent yield is your actual yield that you got experimentally over your theoretical yield times 100. Okay? So this means that in our lab, we ended up getting 87.4 grams. So that's our actual yield. And this happens a lot in chemistry. We don't always end up getting, you would have to be a really good chemist to get exactly 102 grams of copper. Chances are you lose some in the purifying process, in the actual carrying out of the experiment, you lose some of your product. So that's why we always end up with a little bit less for our theoretical or our actual yield than our theoretical yield. If you end up with more for your actual yield, then you have some contamination. You've added something else to your, it cannot be copper because it must be contaminated with something else, because you shouldn't get more than 102 grams of copper. So 87.4 divided by 102 times 100, this gives us 85.9% yield. Let's do another example. Ammonia can be synthesized by the reaction. And ammonia, you've probably heard of that. It's a fertilizer. We use it for our plants. So that's why industrially it's very important to make ammonia. It's a big thing, big money in the industry. And so this is one of the chemical reactions that we use to make it. What is the maximum amount of ammonia in kilograms can be synthesized from 5.22 kilograms of H2 and 31.5 kilograms of N2? Great. So we want to start like we did last time. We have 5.22 kilograms of H2 this time. We want to use the molar mass of hydrogen gas, but we don't have the molar mass in kilograms per mole. We have it in grams per mole. So let's convert our kilograms into grams. And then we say, okay, for every 2.2 grams of H2, we have 1 mole of H2. Now we can use the chemical equation here, and we know for every 3 moles of H2, we have 2 moles of ammonia. Now we want to go back because we want to say what is the maximum amount in kilograms. So let's convert back to grams. For every 1 mole of ammonia, there is 17.04 grams, and for every 1,000 grams there is 1 kilogram. Okay, so you could see that our grams here cancel, our moles cancel, and we are left with kilograms of ammonia. And we can also simplify this because there's 1,000 on the top and 1,000 on the bottom. And so we end up with 29.4 kilograms of ammonia here. Now, let's look at our other ingredient, which is 31.5 kilograms of N2. And let's do the same thing. 35.5 kilograms, or 31.5 kilograms of N2. Of course, we want to convert to grams first, so we can use our molar mass. And we have 28.02 grams for every 1 mole of N2. It's a diatomic atom, so it's 14.01 times 2. That's why we get the 28.02. Same thing for the hydrogen here. It's diatomic. It's made up of 2 hydrogen molecules. All right. So for every 1 mole of N2, I get 2 moles of ammonia here. And now I go back to grams, and I know there's 17.04 grams of per 1 mole of ammonia, and I want to convert this to kilograms, so the grams will cancel out, and I end up with this. So I get 19.2 kilograms of NH3. Now, what is the maximum amount of ammonia in kilograms? Obviously, we have the theoretical yield of 19.2 kilograms. So N2 is our limiting reactant, okay? See, a lot of students, they think that if they see the lesser amount here, 5.22 kilograms of hydrogen gas, then that's going to give you the least amount of product, but not necessarily so, because you see, you get 2 moles of ammonia for every 3 moles of hydrogen gas. So it's all about the ratio, whereas for nitrogen gas, you get 2 moles of ammonia for every 1 mole of nitrogen gas. So it's the ratio and the molar mass of each product that matters at the end of the day. So don't just assume that the lesser amount here would be your limiting reactant. Okay, go ahead and give this a try. This reaction is used to obtain iron from iron ore. And you know, iron ore, we dig it up from the ground. It's very hard to find pure iron. So we usually find it as an iron oxide, and we have to purify it to get pure iron so that we can use for our industrial purposes. So if we have a reaction of 185 grams of iron ore with 95.3 grams of carbon monoxide, and we actually end up producing 87.4 grams of iron, let's find the limiting reactant, theoretical yield, and percent yield. Go ahead and give this a try and replay the video to see if you got the correct answer. So we always want to start with what we're given, 185 grams of iron ore, and we know that there's 159.69 grams of iron ore for every 1 mole of iron oxide here. And now we can use the ratio here. We have 1 mole of iron oxide to produce 2 moles of iron. So 1 mole of iron oxide gives us 2 moles of iron. Okay? Now, we want to go from moles to grams. So we have 1 mole of iron gives us 55.85 grams. And so we end up with 129 grams of iron. Let us do the same thing for our second ingredient, or our second reactant. And we are told that we have 95.3 grams of carbon monoxide. So we have 28.01 grams for every 1 mole of carbon monoxide. And let's look at our ratio up here. We have 3 moles of carbon monoxide for every 2 moles of iron. Now let's convert back to grams. For every 1 mole of iron, there is 55.85 grams of iron. So here we end up with 127 grams of iron. All right. Now, what is our limiting reactant based on this? Well, here's our theoretical yield. Okay, so our limiting reactant will be carbon monoxide. Okay, and then lastly, what is our percent yield? Our percent yield is our actual yield that we got here, 87.4 grams, divided by our theoretical yield, the one that we should get, times 100. And this gives you 87.4 divided by 127 times 100 gives you 68.8% yield.